Let's continue and about understanding what this sigma y means. So sigma y was defined as the smallest sigma algebra containing all the pre-images of all Borel sets by this function y. And we learned that was the fact that this is just the collection of pre-images of all Borel sets. And y was a map from omega to the real line, considered to be a random variable. Assume next that there's another random variable, z. And our question is now, is z measurable with respect to sigma y? So now the sigma y Borel sets are there, and that's kind of the concrete thing, and then the sigma y is now an element there. So we think about these sigma y and Borel as the fixed collection of sigma algebras. Our question now is, when is z sigma y measurable? And if that is the case, sometimes we might write this just to say that z belongs to the measurable functions on sigma y. This is actually the notation that I was using in the autumn in the course stochastic processes. So I was using actually the notation that z is determined by y. So actually I was using this notation in the sense z is determined by y. So z and y are random variables, both can take random values, and we don't know what values they might take on z and y. But we could ask, if we would know the value of y, would we also know the value of z? And that's very closely related to this question. When is z measurable with respect to the information? Remember, this refers to the kind of information of y. And that's where we have a theorem. It's attributed to Joe Doob, the American mathematician that we learned already about the identification theorem. There's also maybe another mathematician that might be mentioned. It's called Sierpinski, Polish name, and there's some little mark somewhere there. I'm not very good in Polish, so maybe I misplaced this, but Sierpinski was one of the famous Polish mathematicians. So there's a school in Poland, and they like in analysis algebra. Poland was really a big mathematics country in, let's say, 1940s and maybe 30s. And there was a famous Banach cafe in Lvov or Lviv. This city is now on the Ukrainian side, so if you ever get the chance to travel to Ukraine, so you might try go finding this famous cafeteria where Sierpinski and well, Stanislav Ulam of the later of the Manhattan Project, so where these people used to hang out, and Banach, where they kind of solved famous problems. So Sierpinski was developing and looking at this question as well. Okay, what is the theorem? What is the theorem? The theorem is that z is sigma y Borel measurable if and only if z is a deterministic function of y for some function f on the real line for some Borel measurable. And that's the theorem. Clarifying what this is, this means that z is a composition of f and y, or it means that z omega is equal to f of y omega for all omega. That's what it means, this symbol here. Okay. And in the lecture notes, we call this Doob's representation theorem. And as you look at the statement, so this theorem really confirms us that the intuition that whatever is sigma y measurable means actually that it needs to be something which is deterministically determined by y. So assuming that we observe the value of y, then we can apply this function f, and then there's no more randomness in z after we observe y. That's the meaning of it. Maybe if you like to ask questions, this could be a good moment. Just shout aloud if you like.
What is the meaning of using sigma y Borel measurable here? Is there some intuition behind using this specific measurability here for z?
The meaning is that well, for Borel, we agree that Borel is kind of the technical condition that we always want to use on the real line. So think about real line. Whenever you have a real line, you always have the Borel there. So kind of it's a technical thing which makes life good, because that means that then you can do analysis with open sets and the usual topology on the real line. So that's why B and R are kind of synonyms. They are always coupled together, R and calligraphic B. The other thing is that we want to ask this, we want to understand what does sigma y really mean. And to understand that, we want to understand that sigma y, we want to know which functions are sigma y measurable, essentially. And this theorem is describing it, that, okay, those functions are precisely what is written down there. So it's the meaning is to understand what sigma y really means. To understand it better, this is a good thing to work on the proof of this theorem. Hopefully this answers the question, or maybe there will be homeworks that bring more concreteness here.
Yeah, kinda. It's a bit unclear still, but maybe it'll get better soon.
Let's go on. Sometimes there's a bit of things unclear. The clouds will fade away later when we kind of walk around, see a bit of facts and theorems and definitions more. So when you get perspective, the sun will shine later on. Don't worry. Let's look at the proof here. How do we prove this theorem? It looks, notice again that it looks like an ambitious theorem. Why? Because there's this for some, so it means existence. How do we prove existence? Proving that something exists are usually demanding in math. And let's see if this is an exception. To start, in this type of problems, which are common in probability theory, it's a good idea to try to start with some simple restricted case first. And the simple case could be that we start with binary random variables. Because if you cannot prove it for binary, then you cannot prove it for more general. So that's why it's usually, and also actually, if you can prove it for this, then there are techniques that we learn that help us to extend a lot. So we start with binary first. So that means that we assume that Z is 0, 1 valued. So there are only 0 and 1 values here, and we assume that Z is sigma y measurable. Then we are trying to look at the existence of this function f. Okay. So in this case, we can write Z is actually equal to the indicator of a sum-set A, where A is the pre-image of by Z of the set which contains only the number 1. We look at this. So it means that the Z omega is equal to 0 or 1. It's 0 if omega is in the complement of A. It's 1 if omega is in A. But A is defined as the pre-image of 1. So then that's why you see why this makes sense. Hopefully that's okay. Yep. Shout it out if this notation is unclear. In that case, I clean this up and we continue a bit here. And then we note that, okay, the set which contains the number 1 on the real line so maybe one picture here that omega is there, the real line is there, there's 0 and 1, and we look at the set A, which is the pre-image of 1. Okay, so what do we know about this set A? It's the pre-image of this set which only contains number 1. This set is a Borel set. Why is this a Borel set? Because it is a closed set, and especially a closed set is a complement of an open set. So that's why this set is a Borel set. This is a pre-image of a Borel set, and because we assume that the Z is sigma y measurable, so then it follows that this is actually belonging to sigma y. That's because we assume that the pre-images of Borel sets by Z are sigma y measurable. Yep. So we conclude that A belongs to sigma y. And what else can we conclude? Then we recall that the sigma y, by the fact that we learned, is actually this collection. That's our fact. And why? What does it imply? It implies that actually A equals the pre-image of some Borel set by Y for some B. And that B is important. So note that this is the existence. So now we got the existence of something. A is the pre-image of something, and then now we have that something. That's where we can grasp, and we keep hold on this set B. What do we do then? Then it follows that Z is actually the indicator of the pre-image of B. And what does it mean? If you plug in Z omega, so it's the indicator of well, it's the indicator of that one, but we can study that Z1 is actually 0 if omega is in the pre-image of the set B, and it's 0 else. Yeah. So, but when is omega in the pre-image? So this is equivalent to saying that this condition is happening if and only if y of omega belongs to B. Yeah. You see that this condition and this condition are the same condition. Omega being in the pre-image, meaning that, okay, y of omega being in the set. And that means that we can also write z as another indicator. It's the indicator of B evaluated at y omega. And that's why we also can write it as the indicator of B composition y. We compose two functions and then we evaluate it as this composition in omega. What are we going to do? We are going to write this as function f composition y at omega. What is our f? F is now a map from the real line to real line, defined by f of x is equal to indicator b of x for any x in the being a real number. This is our function f. Is this function a Borel measurable function? What can we say about the pre-images of f? Take any set C. So, and then we ask, okay, what's the pre-image? So we can actually, I think we did it already earlier, so let's not repeat everything. Let's say that f is Borel measurable. Because B is a Borel set. That's what we can conclude, and that's if you, I think it's related to one of your homeworks, so you can check it yourself that this is true. So let's recap. We assume that z is a binary random variable. We assume that z is a sigma y measurable. Then what we concluded that the z is actually indicator of something, and z is actually a composition of f and a function y. So that means that we have proved this is the non-trivial part of the theorem. Yeah. The other part is, let's say, rather trivial, but this part is non-trivial. We have proved it now for the binary case. Yeah. So we have done the proof for the binary case. Yep.